we're back. I haven't gone very far. So I promised you a theorem. I promised if a sequence converges, then that sequence is bounded. Okay, well let's prove it. Let's let A sub n be a convergent sequence, because we want to show that if a sequence converges, then it is bounded. So let's consider any convergent sequence. If it converges, then it has a limit. Let's give its limit a name. Let's call that limit A. We need to show that this sucker is bounded. So just like what we did in the proof of the multiplication law, by the definition of the limit there is big N, such for a little n bigger than big N, absolute value of an is less than 1. But let's see what that means. Right? We want to get bounds on an. Absolute value of an minus a is less than 1 means that an minus a must be between -1 and +1. So an must be between a minus 1 and a plus 1. And so, apparently, it looks like a minus 1 and a plus 1 are straight up upper and lower bounds on the sequence an. But only as long as little n is bigger than big N. But if you look at the definition of bounded, we need upper and lower bounds which hold for all n, not just for all little n bigger than some big N. So that's not good enough. So let's deal with those little n that are less than or equal to big N, since we need upper bounds on all of the terms. So here, let's play it this way. Little m, let's let it be the greatest integer that happens to be less than or equal to big N. Then, the set of set A1 through AM, that's just a set of m numbers. There might be repeats, so it might be a smaller than m set, but that set is finite. Finite sets are bounded. Any finite set has a biggest element. So this set has an upper bound, call it U, a lower bound, call it L. Let's let U prime be the max between the upper bound that works for the first finitely many terms and a plus 1, which we know works for the terms after it. Let's let L prime be the min between the lower bound, which we know works for the first finitely many, and the lower bound, which we know works for all numbers after some threshold. So let's play this game. You could probably do it from here. So let's consider any n in n. We want L prime less than or equal to an less than or equal to U prime. Let's see, for this fixed natural number n, either little n is less than big N or little n is bigger than big N. In the first case, well, in the first case, we see that little n is less than or equal to big N, but m is the greatest integer less than or equal to big N. So little n is less than or equal to m. Well, but check it out. Since little m is less than or equal to little m, we get this step. But L prime is the min between L and a minus 1, so it has to be less than or equal to L. U prime is the max between U and something else. So U is less than or equal to U prime, so we get the inequality we want. In case 2, in the case that little n is bigger than big N, then we know from this stuff that an is less than a plus 1, but bigger than a minus 1. Oh, and that should have been making you upset. Those should be loose inequalities, not strict. So an is between a plus 1 and a minus 1. Well, a plus 1 is less than U prime because U prime is the max between a plus 1 and something else. Similarly, a minus 1 is bigger than or equal to L prime because L prime is the min between a minus 1 and something else. Either way, we get L prime strictly less than a, strictly less than U. So an is bounded. We even found strict bounds, not that that matters. Nice. Cool. So there are two last results that I want to get. The first one governs inequalities. So let's suppose you have a sequence an and bn. Suppose an converges to a, bn converges to b, and an is less than or equal to bn. Then the same is true for the limits. The squeeze theorem says if for all n, an is less than bn is less than cn, and an converges to a and cn converges to a, that's not a typo, those are both the same letter, the limit of an is equal to the limit of cn, then bn also converges to a. So let's prove the first one first and the second one second. So let's let an and bn be sequences. Let's assume that an is less than or equal to bn for all n, that an converges to b and an converges to a, and bn converges to b. Let's suppose for the sake of contradiction, well, that's what we need to show. So let's suppose for the sake of contradiction that a is bigger than b, because that's the negation of what we want to show. But if a is bigger than b, right, I want to come up with a choice of epsilon, a positive number that will measure this contradiction. So if a is bigger than b, I guess that means that a minus b is bigger than 0. So let's take epsilon to be a minus b. Either that choice of epsilon will work, or it won't, in which case we'll figure out that we need to divide by 2. I guess that's what we've always done so far. Eventually there will be circumstances in which we need to divide by 4. So we'll see what happens. So on the one hand, you might have just paused it, said, Chris, I'm done listening to you, I'm just going to write my proof, and then listen to your proof and see if it's the same proof. That's fine. So let's let epsilon be a minus b. So we know that an converges to a and bn converges to b. So there exists some big N, such that for a little n bigger than big N, absolute value of an minus a is less than that epsilon, and absolute value of bn minus b is less than that epsilon. So, well, let's see what that means. Maybe I'll write an intermediate step. So, an minus a is less than epsilon. Well, let's solve that inequality like we've done a few times. An minus a is less than epsilon in absolute value. This will become minus epsilon less than an minus a. Oh, I'm getting rid of the absolute values. I shouldn't be drawing them. Is less than epsilon. So that means a minus epsilon is less than an is less than a plus epsilon. Cool, fair enough. Happy, happy, happy? Similarly, since absolute value of bn minus b is less than epsilon, I'll draw the arrow and I'll let you fill in the things between. We get bn minus epsilon is less than bn is less than b plus epsilon. But check it out. An is less than or equal to bn. So, an minus epsilon is less than an, is less than or equal to bn, is less than b plus epsilon. So, a minus epsilon is less than b plus epsilon. So subtract a, add epsilon. Absolute value of an minus b is less than 2 times epsilon, which is equal to 2 times a minus b. So, we conclude a minus b is less than 2 times a minus b. Is that a contradiction? I mean, it's not. Multiplying something by 2 doesn't make it smaller, it makes it bigger. So there's no contradiction. But, I mean, you know what I'm about to do. I'm going to divide the quantity that I got to choose, I'm going to divide that epsilon by 2. Let's see, I gave myself space on the next page. Thus, a minus b is less than a minus b, a contradiction. Am I off the page? No, I'm not. I think I'm even in focus, so it's hard to tell from where I stand, as you know. Cool. So, this is a contradiction. Thus, it must be that the thing that we assumed is false. What did we assume? We assumed that A is bigger than B, so that has to be false. So yeah, B is bigger than or equal to A, as we claimed. So that completes the proof of claim 1. Let's prove the squeeze theorem. So let's start with a false proof. So basically what I'm going to do is I'm going to read through this false proof. You should pause it after I'm done here for, I don't know, a couple minutes, and see if you can figure out what's wrong with this proof. So let's suppose that AN, BN, and CN are all sequences. Let's assume that for all n, AN is less than or equal to BN is less than or equal to CN, that AN converges to A and CN converges to C. Cool. So that's like all of the assumptions of the claim. If Bn happens to be the limit of B, then from part 1, well, AN is less than or equal to Bn, AN converges to A, Bn converges to B. So AN is less than or equal to B. Bn is less than or equal to Cn for all n, Bn converges to B, Cn converges to A. So B is less than or equal to B. Well, if A is less than or equal to B is less than or equal to A, then basically by the trichotomy law, B is equal to A. Thus, B converges to A, as we claimed. But I told you something was wrong. Take 5 minutes, figure out what it is that was wrong. I'm not actually going to be quiet. You're going to be responsible for hitting pause yourself. Okay. Cool. You're back. Did you figure it out? Yeah, that's right. That line underlined in blue isn't justified. We assumed that the limit of Bn exists. But we know that not every sequence converges, and if we read the statement of the squeeze theorem, there's nothing in here about assume that Bn is a convergent sequence. So that proof is definitely of something. It's a proof that if AN, BN, and CN are sequences, AN converges to A, CN converges to C, AN less than or equal to BN less than or equal to CN, and BN converges to something, then that something that BN converges to has to also be A. So it's not like a proof of nothing, it's just not a proof of the thing we claimed that it was a proof of, because we assumed something extra. So let's do a correct proof. So let's go for it. Let's let AN, BN, and CN be sequences. Let's assume that for all little n in big N, AN is less than or equal to BN is less than or equal to CN, that AN converges to A and CN converges to C. So here's the game that I'll play. So maybe I'll picture a proof. So there's this number A. So I know that by taking little n to be big enough, I can get, there's a length of epsilon, I can get AN to be in that neighborhood. Similarly, Bn converges to A, so by taking little n to be big enough, I can get Bn to be in that same epsilon neighborhood. And I don't know that it's in that range specifically, it could be down here. But that means that, Cn. But wait, Cn is less than or equal to Bn is less than or equal to An. So that means Bn has to be somewhere in there. But everything in there is within an epsilon of the target A. So that means the absolute value of A minus B should be less than epsilon. So that kind of is a proof. No, we just need to write it down. Consider any epsilon bigger than 0. AN converges to A, Cn converges to A. It follows that there exists some big N, such that for all little n bigger than big N, AN minus A is less than epsilon, and Cn minus A is less than epsilon. So solving this inequality for AN, solving that inequality for Cn, we get A minus epsilon is less than AN is less than A plus epsilon, A minus epsilon is less than Cn is less than A plus epsilon. And now let's combine that with the assumption AN is less than or equal to Bn is less than or equal to Cn. So AN is less than or equal to Bn is less than or equal to Cn. an in ton is less than or equal to a minus epsilon. Cn is less than a plus epsilon. And maybe I'll add a little bit more detail here. This is, I mean, enough detail that I would be happy with this amount of detail in a submitted proof, but maybe for the sake of exposition, let's explain more if you don't see how to go from this to that. So that means a minus epsilon is less than bn, right? I don't actually care about an and cn anymore. So minus epsilon is less than bn minus a is less than epsilon, and so absolute value of bn minus a is less than epsilon. But that's exactly what we need. So if you like, this step was one of the absolute value identities from a while ago. Cool. So that completes the lecture on limit laws. I think I'll stop here. I'm going to post another video that's going to be like, how should you think about some of the homework problems, which I'll let you watch or not watch as you prefer. Thank you for listening. Let's see, this one has been another 16 minutes, so this has been like a 45-minute lecture. Groovy. Talk to you again.